The idea of this task was to give you a quick recap about linear algebra, basics, fundamentals, and matrix computations. And especially, I want to emphasize the difference between element-wise multiplication and matrix multiplication, dot product, matrix product. So first, let's see what we are given here. We are given 3 matrices, and here we call them 2, 3 matrices. This means that they have 2 rows and 3 columns. And this is also very important later because we really want compatible matrices. For example, you couldn't add 2 matrices whose shapes don't align. That just wouldn't work, wouldn't be defined. So let's see what happens here. All those operations that we face in this expression are element-wise. So if we fill in what we have here, so this is A, this is B, this is C, then we can see that we're supposed to apply a multiplication here, but this multiplication is element-wise. So it's 3 times 3 equals 9, 3 times 5 equals 15, and so on. The same over here. Here it's a bit tricky because we have this minus, but we just make from this minus a plus, minus 5 times and convert it to a plus or addition. But we have to multiply everything by minus 5. So minus 5 times 1 is minus 5, and so on. And then we get the second line. And for the third line, we just have to do an element-wise addition. So this 8 here is the result of 9 plus 4 plus minus 5. And for example, this 0 minus 2 plus 0 is this minus 2 over here. So element-wise, so far so good. We just have scalar multiplication with a scalar value over here, and everything goes as we expect. If we have a look at the next task, we have another operation here that's kind of new, and this is the transpose operation or transposition. And it's important to understand this because it will allow us also to do some matrix multiplication later, despite not being given shapes that would allow to do matrix multiplication. I'll explain what that means in a minute, but basically this transpose operation converts a 2-3 matrix into a 3-2 matrix. So suddenly, if we have a look at this transpose operation here, we get 3 lines and 2 columns, or 3 rows and 2 columns instead of 2 rows and 3 columns. And how does it work in detail? Well, if you have a look at this expression, then first we fill all the matrices in again and do this subtraction here, just element-wise, no problem. So we have this matrix over here. And now we want to transpose it. And how does it work? Well, we have an element with the coordinates I, j, and it gets converted, or the position gets converted into ji. So it's swapped. For example, this element over here has the coordinates 1, 2, because it's in the first row, second column. And it gets converted into 2, 1. So second row, first column. Something that maybe helps you to memorize this is to aid this visually as a mirror flip. If you want to have a symmetry axis here, then everything gets flipped. So the 0 gets flipped over here, the minus 4 flipped over here, the minus 1 flipped over here, and so on. So maybe that helps memorizing what we are doing or visualizing it. But this over here should be the clearer definition. So the effect is clear. We now get a different shape, but the same rules apply again. Scalar multiplication, do this with every element. We get this one. Subtraction. Here we convert the subtraction into an addition again by just multiplying everything with -1. And yeah, then we do the element-wise addition and get the result. So for the next task C, I want to give a quick motivation of why we are doing this. Why this weird product? I'll explain to you again what this exactly means in a minute, but why this weird product? Why not just take element-wise product, for example? Well, element-wise product is a bit boring because we want something that allows values in both matrices to interact with each other in a more flexible fashion. So we want more interactions between the elements in the matrix than we would just have if we are doing a 1-1 interaction in an element-wise matrix. So if you would consider the element-wise operation over here, then you only multiply those elements. So for this one element, you only have 2 elements that got in there. But how is the multiplication of matrices defined? Well, you have one matrix and another one. And in order to compute the result at a certain location, over here, for example, you actually need to do an addition of products. And you do it the following way. First, you determine the row again, and you apply it here. Then you extract this row, and then you determine the column, and you apply it here, and extract this column. And what you then do is you multiply element-wise in this direction, but you add the products, and this yields this result. So it's extremely complicated in comparison to what we did above here, but well, it's a better way to multiply matrices because it helps in a lot of applications. It gives you better interaction. We have, if you come from a mathematics perspective, we have the possibilities of defining a group because you have a neutral element, which is the identity matrix. You have sometimes have inverse elements. Wonderful, and you can work with that. And we'll really need that later in many applications, especially if you want to consider working with neural networks, for example. This will come in handy. Let's now see what we are doing here. Why is the task, A multiplied with C transposed and not just A multiplied with C? Well, that wouldn't work actually because the shapes are incompatible. You need a different kind of compatible shape structure than you have for matrix addition, for example. For matrix addition, you would have liked to have 2 matrices with the same shape to do this element-wise stuff. But here it's just important that this width and this height match up. So the width of the first matrix and the height of the second one have to match up. And this is just isn't the case if you consider what we had here. I think it was 2, 3, and again 2, 3. This doesn't work. You really need this and that value to match up. And what we do here is we just transpose the whole thing. So it becomes, where is that? It becomes 3, 2. And then these values match up and you can do the multiplication. So again, this transposing step over here should be clear by now, but maybe let's do one quick computation of one element to see that you all know what we're doing here. Let's compute this element over here. So we are in the first row. This is here. And in the second column, this is here. So first it's 3 times 5 is 15. 5 times minus 2 is minus 10. And 2 times 0 is 0. So we have 15 minus 10 plus 0, that's 5. And this is exactly what we have here.